In this lesson, we want to talk about the technical components that make up a digital twin platform for urban logistics, such as it has been designed in the LEAD project. To give an overview, here we see the technical entities that are necessary to implement the required functionalities that we have identified in the business process. And in the graphic, you can see that three main layers have been identified. So there's the physical world. As before, we have a data and model management system and a storage system. And the second system is also divided into two more complex components, which is a data ingestion system and a modeling management system, which we will have a look at in detail. As before, we start with the physical world because we have technical elements in the physical world. So these are data sets that can be retrieved on city data, on contextual data. These are Internet of Things, devices that can be accessed and manipulated. These are sensors that we can use to obtain information. And these are also APIs that are provided to us where we can obtain information that we can digest in our digital twin. The second component is the data and model management system. As the name says, its purpose is to manage different models, and we will have a large variety of different models and simulations that we can run, and also to manage data sets. And there we will also have a large variety of different data which are qualitatively different, so they have different types, but also there will be a certain quantity of data that need to be managed. If data is arriving step by step, maybe on the level of seconds, but in some cases also just in the frequency of days or other timescales. And finally, one of the important tasks of the system is to maintain the interactions between different models if we need outputs from one model as the input in another model, but also defining which data can interact, which model, which data can be combined by using certain modeling components, and so on. Specifically, the data ingestion system has the task to manage a large variety of devices and protocols for data ingestion. Here we have different devices that can go from traffic lights to measuring systems for the content of certain containers. This can be signals from individual vehicles that are sent to the system. And today we have many different protocols, many different approaches of transmit this information. And if we want to have a very generic digital twin that can respond to many different use cases, we also need to support a large variety of these different devices and the different protocols that are assigned to them. So for this purpose, we have a device manager and a protocol manager. Also, each of these different data sets that we will obtain, they have different types. So for instance, some data sets, they represent a table of individual trips of a vehicle. There are some data sets that represent temperatures by hour. There are other data sets which may describe the inflow into a certain distribution center by hour or maybe by the day of the week. So there are different kind of data sets. Also, for instance, network data, which are more static information that we need to combine and classify, and we need to know if we have some data lying somewhere or arriving somewhere, what it is and how it can be used in our system. So we need this contextual semantic information on all the data sets which are managed by the semantic manager. And finally, we have the context entity manager, which will provide the information on all of these different data sets, dependent on in which context they are used and for what, to the model management system. The main component in the model management system is the model library manager. And here we have already seen in a previous unit that we will use many different models to respond to different use cases in urban logistics. As a recap, we can have a look at the modeling library as it was already presented in a previous unit, where we have models on the operational, short-term, tactical, and then strategic, very long-term scale, which respond to different business cases. And we have also the tools to calculate key performance indicators that then assess, for instance, the emissions or congestion or costs of different use cases. These models have different inputs and outcomes. And one of the tasks of the model management system, specifically the model integration and orchestration component, is to know which outputs come from one model and which inputs go to another model, and then it needs to know how to connect these two. And for this purpose, it is useful to have the semantics on the different data types, because there we will know which models are compatible in terms of the abstract information that we have on the different data sets that are needed or provided by these models. Another component in the model management system is the scenario manager, which basically manages or contains different configurations for the individual models, saying, for instance, if we want to deploy an urban consolidation center in a city, this scenario manager could know how it needs to configure these individual models and simulations to have a scenario for 2022, then for 2030, 40, and maybe even 2050. And dependent on the context, different information may be needed, different predictions may be integrated into these models. And once these models are configured in a correct way, so they are runnable and they will not produce any errors, they can be executed in an execution environment, which will also be provided by the model management system, with certain challenges that enough of computational power needs to be available and so on. And finally, there's the decision system as part of the model management system, which can then evaluate the outcomes of multiple simulations, of multiple scenarios, and obtain the decisions which are optimal given certain inputs. And this is then what can be communicated to the final user. All of the model components that we have discussed so far, they need to store data. So there's incoming data coming from the physical world. We have preliminary modeling results coming from one model, which are then transferred to the next model. And at the end, we want to save our final analysis somewhere. And for this purpose, we have the storage system, which needs to be available to all these different components. It needs to be accessible in different ways. And there are additional challenges. For instance, when we work with sensitive data and we are talking about encryption of these data sets so they can be used on this platform in a secure manner. To conclude, we have seen that there is a large set of components that are necessary to set up the technical architecture of a digital twin. And this is only the abstract formulation of these individual components. However, one needs to think about how the implementation can be performed, and there, during the project LEAD, we have found that most of these requirements can be covered by already existing open source solutions, and they have been identified during the project. The challenge remains to connect these existing building blocks, and for certain specific developments in the LEAD project, we will see more detailed analysis in the following lessons.